Actually, before we start writing our grow algorithm down here, what we are going to do is to write our run script method first. So remember, the lines that we write here are the ones that are actually going to be executed each time that the C# component is running Grasshopper. So we are going to do this first in order to get some context how this program actually works. And of course, the first thing we need to do is to define our tree object as a global variable down here. And now we are ready to write the run script method. So let's forget these lines for 1 second. And how is this working? So basically what this is doing, this is very similar to the previous example. So if reset is true, which happens when we press the button here, in that case, we are going to create a new tree object like that. And any other way, in any other case, what we are going to do is to call this grow algorithm that it's empty. That this is not going to do anything by the moment. And this is going to happen when we set the timer in Grasshopper and it starts calling the C# component over and over again. And we are going to add another condition, which means, this only happens when reset is not true and also when the tree hasn't been initialized yet. And this will only happen the first time that we close the C# component and we compile the program for the first time. So this is just to avoid an error. So let's close this and see how it looks like. Okay, so first, no errors, which is of course nice. And now if we click on reset, we can see that we have our tree trunk here. So why is this happening? So remember, we are just running our C# component once. So this is not doing anything because the grow method is empty. The only thing that we are doing is calling the tree constructor here. And if you remember, what we were doing with that constructor was basically saying, okay, I'm going to define my root from the origin and with this initial direction, and then I'm going to keep adding new branches to this root, let's say in the same direction, until we have one branch which is close enough to the first target here, which we are checking with this close enough method here. So that's what we are doing, and it seems like it's working because it's adding new branches until the first one is in range of the first target, and now the ramification can take place, or the so-called space colonization, of course, once we define our grow algorithm. Okay, so now we are ready to start with our grow algorithm that we are going to call each iteration of the program as we just said here. So each time we call this method, the first thing we need to do is to check our targets. So what we are basically doing is using a loop, using this for each loop to go through all targets that we have. And for each target, we are also going to loop through all branches. And the first thing that we are going to check is if there is one branch that is so close to that target that it's already reached. In that case, if the distance between that branch and that target is closer than this parameter, that target is already reached. Okay, otherwise, what we do is we make that branch the closer branch, and we will keep looping through all branches to see if there is actually a branch that's closer than the one that we already found. And then we are going to finish this loop of our branches, and what we are going to see is if for that particular target there is a close branch, then in that case what we are going to do is first to increment this count property of our branches that we already defined, if you remember, and what we are also going to do is to modify the branch direction by adding the vector that points to this closest target. And we are going this because later on we will define a new branch that taking as argument this as parent branch. Okay, so now we are done looping through all of our targets in our tree, and the next thing that we have to do, hopefully here, is basically to remove the targets that are already reached, so that we don't consider them again in our grow algorithm, like that. So basically, if we said that any particular target was already reached, then we are going to remove it from our list with this method. And now we are finally ready to define how we are going to grow our new branches. So what we are going to do is, of course, to loop through all of our branches, and we are going to say, okay, if any particular branch is the closest branch to any of the targets, then in that case, what we are going to do is, of course, first to reduce the length of that branch, because remember that first what we had done up here is basically to keep adding this closest dir vector so that our branch direction points more and more to the closest targets. So we are going to reduce that length first here by dividing it by the number of closest targets, let's say, so that every time we have similar vectors in terms of length. And then we are going to add some kind of randomness into that direction vector, so that the tree looks more natural, let's say. And this is basically how we deal with random numbers in C#. So the first thing that we always have to do is to create, or better said, to initialize this random object like this. And now we have to define our coordinates of the random vector like that. So first we call this nextDouble method, which generates random numbers between 0 and 1, and I'm going to scale this number because I don't want that much randomness. And now when we have our coordinates here, I just basically add this random vector into our original direction, and we are finally ready to define our new branch just by taking as input, as argument, this parent branch whose direction we already modified, as I said, so that it points to the closest targets and so that it also has some kind of randomness. And now finally we basically add the new branch to our three branches, and we also reset our parent branch so that for the next iteration the counter of the closest targets is set to 0. Okay, so I think that was it, and now we are ready to get back into Grasshopper and test if this grow algorithm is actually working. So of course the first thing I'm going to do is to do this Rhino window, this Rhino viewport really big, because I'm very excited about this. So if I click on reset, you can see, I mean, it's not that nothing is happening, but if you take a closer look, you can see that we are just adding a new branch into our tree trunk. And why is this happening? So this is happening because we haven't defined our timer in Grasshopper yet, and the timer is the one that is going to call the C# component again and again and again, so that the tree grow method is executed all those program iterations. So of course, let's define the timer now, finally. Let's set an interval of, let's say, 100 milliseconds. And now if we connect it to the C# component, we can actually see how this space colonization, or how this tree growth actually takes place. And I think it's beautiful in my opinion. So let me reset it, not just to check if this is working, but just because it's beautiful to see how this algorithm actually works. Okay, so before we finalize this example, we are going to make some changes so that our animation looks even more appealing. So first I'm going to hide my box and my points from Grasshopper. And okay, now it looks better, but what I also want to do, of course, is to display in Rhino the points, or the targets better said, that haven't been reached yet. I mean, this is beautiful. So of course, one way that we could do that is, as in the previous example, to create another output parameter and basically assign those targets or points to that output parameter in C#. But since we are not using those points later on in Grasshopper and we just want them for the visualization, I'm going to show you a trick in which with which we can display objects in Grasshopper or in Rhino directly from the C# component without assigning them to any output parameter. And I'm sorry, and we have to do this outside the tree class, of course. And this is how we do it. So we are going to call this method, and you can take a look into it into the Rhino common documentation again. And what we are going to do is to loop through all targets that are included into our global variable tree, and then we are going to call this method drawPoint to draw those targets. And remember, the targets of our tree are the points or targets that haven't been reached yet, because otherwise we would have removed them from our tree. So let's see how this new method or new subroutine is working. So let's reset our algorithm, and of course let's make this a bit bigger like that. And now if we click on reset, we can see how we are displaying our points in Grasshopper or in Rhino, and how they are getting hidden whenever a branch reaches those targets. So now we can see, okay, it looks really nice, but there are some targets that aren't being reached by any branch. Okay, I mean, it's not that bad, because we have a very nice looking tree in my opinion, but I don't know if we really want all targets or leaves to be reached. One thing that we can do, of course we can change those targets, but that would be cheating more or less. So what we are going to do is to come back here to this grow method once again, and here in this line what we are doing is to set the new branches to look to the new closest targets to that branch. And here, if we basically modify this vector by multiplying it by 2 or even by 4, what we do is that the new branches are less similar to the parent branch, and they point more to that closest targets. So in that case, our branches should be, let's say, more focus oriented in reaching those targets. So let's see if this works. Let's get back to Grasshopper and click on reset. And okay, it seems like all targets are being reached so far. It looks nice, perfect. And yes, all targets have been already reached. And I think that now finally we are done with our space colonization algorithm.